So yeah, I'm going to give you a talk on our journey in banked into protocol buffers. It's probably not going to have the high-stakes drama of Avengers Endgame or average Game of Thrones episode, but I'm hopefully going to tell you a story about how we started from nothing and got to where we are, and hopefully where we're going. On a side note, the guy I was meant to be doing this talk with, Aaron, unfortunately couldn't make it today, so you just have little of me. But he is responsible for a lot of the work that went into this, and also some of our build tools that we get on later. So thanks to Aaron, who would have been here. So about me, this is some of the places that I've worked. I'm the tech lead on the Kuiper team. All of our teams at Banked are named after celestial bodies. Basically, we're the Golang platform engineering team. We build the standard SDKs that all of the engineering teams use, and some generic services as well. You can find me at all of these places. And of course, so Banked is a payments company, and Tom, who I had a meeting with earlier this week, basically summed it up really well, was like, we basically move the money. And we do this using the open banking specification. You can think of it kind of like a OAuth kind of flow for making a payment. Instead of when you go to a checkout, you enter your credit card information, you instead go to your banking app and authorize the payment through that flow, and then we get a token and permission to then move the money. So that's basically what Banked is and what we do. We're building products on top of that, and our checkout is one of those. The main benefit for consumers is the security. You're not entering credit card information all the time. But for merchants, the money moves instantly, and it's a much lower cost for the merchants as well. So everybody gets a win-win out of it. Of course, we are hiring. We've got a lot of interesting roles coming up in Banked. It's an exciting time at Banked. We're scaling up. There's lots of things to build, lots of interesting problems to solve. So if you're interested, our hiring positions might all be on GitHub, but they might not all be on GitHub. So if you're interested, come and have a chat to me or any of the Banked team, because we've got a few people here afterwards. OK, so when I joined Banked, we were a very small team. I think I was the second hire, I think. Our team was about 10 engineers. We were in one engineering team. And we basically just finished the proof of concept for what Banked as a product was going to do and what it was going to be. And we were just starting to flesh stuff out. And this was at the height of the pandemic as well, so things kind of slowed down around that time. But we noticed that we had some errors. So as I mentioned, Banked is a payments company, so we talk to banks using this open banking protocol. But even though there's a spec, banks are different. They like to do things a little bit differently. They're all like their own little unicorns. And we wrote this SDK, this Banked open banking SDK, to basically take some of that pain away into talking to banks, and that gets integrated into our payment service and use our checkout. But the main issue is that whenever errors happened, some banks would return very different errors for the same kind of thing. And we needed a standard way to represent this error to our users who would just get an unknown error. So we needed something straightforward. And you might be thinking, well, we've got this standard SDK. We could just put a nice error type inside that, do all of the logic inside the SDK for talking to all the various different banks, and that would be the problem solved, right? It gets imported into our payment service. We get to surface a nice error to the user, and everything's fixed, and it's fine. But it's not that simple, because we, like all good startups, have a monolith. Ours one is the Rails variety. That's basically where currently all of our business logic sits. It's also our public API. We're in the process of decoupling this right now, but it exists, and it's going to hang around for a long time. That's the problems with monoliths. So really, we had to define this error type in several places. We had to define it in our Golang SDK. We had to define it in Rails. We had to maybe even define it in our TypeScript front end as well. So we were having some problems. So we needed a hero to come and save us on our journey. So enter protocol buffers, where basically we could define that error type once and have that code generated, and we would have it for all our various different languages there for us. So what is protocol buffers? I'm sure most of you know, but it's basically a way for serializing structured data. It's meant to be language and platform agnostic. It's meant to be extensible. You use code generation to generate out all the various different types you need for all the various different languages you're going to use. It's meant to be compact because by default, it'll use a binary messaging format, though you don't have to use that if you don't want to. And if you do use that, it's fast, but it's kind of up to you if you use it. And it supports all of your big name languages, like all of those there. And I think more are coming. If the language you used isn't there, like maybe you have some Rust in your ecosystem, there will be a third party that does it for you. So we'll walk over briefly like what a protocol buffer file looks like from top to bottom. So at the top, you define your syntax. There's two versions of Proto that you can use. There's Proto-2 and Proto-3. Proto-2 is an old one. Don't use it. It has some features on it that didn't work out very well, especially in the Golang ecosystem, around optional types and required types and stuff like that. So just use Proto-3, but it does have some of the features of Proto-2 as well. At the top, on the second line, we've got some Go-specific options. So we have a way to specify the Go module that we want to generate the code for. So we just give it a standard like module name. Then we have a package. So like a lot of programming languages, you can put things together in like nice little neat packages or modules, depending on what you want to call them. You can then therefore import them. So I've got a little example of how you can import them. And the import that I've put in there is to one of Google's types that they've written, which is a timestamp package, where they've written like these common message types that you can import to represent very, very common types. And they're called the well-known types, and they're documented up there. So the next part is the message. So you can think of this akin to like defining a struct. In Golang, for example, there's some conventions around how you should name these, so title case or Pascal case if you prefer. You just basically give it a name and a same name. That makes sense. The field number is probably the most important part of your protocol buffer file. So when using the binary message format, you're not going to be sending the field names over the wire. You're just going to be sending an ID and a value, because that's way more efficient to send than a name. So basically, you have to give all of your fields an ID number. They don't have to be in order. They can be any numbers you want. But whilst doing the research for this talk, and I was reading the documentation on the Protocol Buffer website, they actually give some nice hints. So the numbers 1 to 15 only take up 1 byte in the binary message format. So for stuff that you're sending around a lot on messages, common stuff that are always going to be on a message, give them a number between that value, because that's going to be the most efficient way to send them. And anything that's like not sent a lot, go from 16 and above, because they all take up 2 bytes. And they also say you should also leave some gaps. So instead of just taking up the numbers 1 to 15 completely, put your most common fields in like 1, 2, and 3, and then leave a gap, so you can put new common fields in there later on down the line if you need to. Okay, so the field name is actually mostly here for humans, so we can identify the field, really, on the other side, but that's only for the binary message format. So if you're using JSON, so you can encode protocol buffers to JSON, the field name is really important, because that's going to get sent over the wire, of course. So it's a good idea to probably not change these. Just like field ID numbers, you don't want to change those either. So try not to change these either, because you can get into a real bad time. So field types. Protocol Buffer supports all your standard types, so strings, ints, that sort of stuff. And you can also like embed or include other types in your messages. So for example, here I've got a foo type, and then a bar type, and that has a foo field on it, and that uses the foo message type. So that's basically nesting messages inside other messages. Okay, so package structure. So this is just a best practice, really, and that is using version subdirectories for your packages. So if you're organizing something like this, so you've got a foo and a bar package, inside that you've got bat and baz. Let's say you're going to need to like create a new version of one of these messages. So maybe bat has a message type in it, or baz has another message type in it, and you want to change that message type. You need to completely refactor it and change it. That would be backwards incompatible. So other than creating a brand new message type inside that same package, it wouldn't be very easy to figure out how to nicely organize that stuff and have a good representation of the data structures. So instead, you put them inside a v1 sub-package. So then when you come to do a v2, to avoid breaking changes, you basically have something that looks like this. So then it becomes really clear when you're importing packages at different versions, what versions you're using. And we'll see this when we do the demos later with Go code, that you're importing the version 1 or version 2 of the message type, so you know what you're using. And you can slowly phase out the version 1 of the message eventually as you update all of your services to use a newer message type. So how do we generate protocol buffer code into language code? There's a tool called Proto-C. You basically you just install it. If you're on Mac, it's just brew install. I'm sure if you're using Linux, there's a package manager out there, or you can just download it straight from GitHub. This basically is responsible for compiling all of the protocol buffers into whatever language you want to use. But the first argument that we give it is this -I. You have to tell it where your protocol buffer files live. Proto-C is very honest about the fact that it is quite a dumb tool, so it doesn't figure out relative and absolute path directories very well. So it kind of wants you to be very specific about where your stuff lives. Same for go out. So here we're telling Proto-C to basically generate Go code, and we want the out of that to go into our current working directory. But you do need another tool to do that. So you need protogen go out of the box. Proto-C won't generate Go code for you, so you need protogen go to do that. And then you obviously need to give it the protofiles that you're going to generate. And now we'll do some demos on that, provided I can get this to work. Displays. I think that's probably the wrong way around. Okay, so hopefully you can see that. Yeah. So this is our first demo. So we're just going to do something really basic here. Basically, I've already got Proto-C installed and protogen go installed. So all we're basically going to do is just going to run this command here. And this is the proto file that we're going to generate. It's like that error insufficient funds thing that we mentioned before. I'm just going to run that. Oh, and I'm probably not in the right directory. There we go. And I'm still probably not in the right directory. Oh. Okay, there we go. Okay, I didn't say my prayers to the demo gods very well. Okay, right, there we go. So now we've got some generated code. So it's in this github.com banked directory in here, and this is the generated code. Obviously, it's generated code, so it's not going to look the best, but you can see that it's generated a type, Go type, and we've got our fields on there that we're looking for. And it's matched this like github.com banked GoFCon 2022 demo 1 package import path. So that's the directory structure it's created. Okay, so next what we'll do is we'll complicate it a little bit. So we'll do some imports. So now in our insufficient error funds message type, we're importing a new bank.payment.amount. So it's probably useful that you're going to create common types that want to represent common values that you use across your engineering teams and your domains. Inside banked, it's very likely that we're going to want to represent a payment amount, a refund amount, any kind of like monetary transfer. So it makes sense to create a common type for that. And we're also importing the Google protobuf timestamp in there, so we're just putting a timestamp field on here. And then up here is where we define our amount type. So this is in the same package, it's in a banked package. So we'll just go and co-generate that now. So now the Proto-C command gets a little bit bigger, because I have to tell it that I want the files in my local directory, but I also want to include the Google well-known types, which automatically get installed for me when I install protocol buffer into this directory. So you'll look in here for those as well. And I also need to tell it that not only do I want the payment proto, but I also want the amount proto as well. So if I run that. And now we've got that code generated in here. And if we go and look at it, we've now got our amount type. Great. And then we've got a payment type. And that payment type uses that amount type. Oops. And it uses that Google timestamp type as well. So how does this look when you actually want to create a message? So you'll also notice that the import path is a little bit messed up here because you're doing like your local module path plus that generated code path that it's got there. We'll fix that in a minute. But basically, we just import the code and initialize our struct as normal. And what I'll do is I'll show you what the JSON output of that looks like, because looking at the binary message format wouldn't be particularly useful. Oh, and I'll pipe it into JQ as well to make it look a little bit better. So you get some nice little JSON out of that. So we want to fix this output path, right? So I haven't really changed anything in the protos at all. The paths, the Go packages, inputs are all the same. Everything else in here is the same, except we're going to change our proto output. So we now have to pass this other Go out option to Proto-C. And I'm going to tell it I want you to generate the code here. And I'm also giving it this source relative argument, which basically says generate code relative to this directory. So it's not going to put everything into like that github.com banked like directory paths. So it's going to sort all that out for us. So we're just going to run that. And also I'm now using this find command to also make it a little bit easier to give it the path to all the proto files as well. Okay, so now we should have some code inside this Go package that's a little bit neater. And the imports in the main Go file is now also a little bit neater as well. So we don't have any like double import, like doubling up of that github.com banked path structure on here. And again, I'm just going to do the Go run main.go in there, just prove that it runs. But this could probably be a little bit better. So I am actually going to clean this up a little bit, though. So, okay, so again, I haven't changed any of the protos. These are all exactly the same. Nothing different here. But now we're just going to like tell Go to output into the same directory that all the proto files are in, and then things will look maybe look a lot neater. So now we get new proto files that are all generated in the local directory, same as the proto directories are. And now that actually makes the importing path a lot easier. We're importing demo 4, and then we can just run the code. If I was in the right directory, because I've moved the command into a command folder as well, and then get the JSON. So easy. I think the last demo is on at this point is restructuring the Proto-C packages so they fit into that recommended folder structure of having version sub packages. So I've now created a bank directory. We've now got a payment directory inside here and a v1 inside here, and I'll get rid of these generated files as well. So I've just moved things around, so things still have this package banked on it, but now it's called bank.v1. And this one is now called bank.paymentv1. The Go package up the top basically now has demo 5 banked payment v1, and now the package name it's going to generate it as is payment v1, and the same applies to the amount up here. So it's now into a banked v1 package, and it's called banked v1 instead. And the command, this won't work until I generate the code, obviously, but the imports will look like this. So now we can just run this Proto-C directory. And then all of the code now gets generated, and it all lives in the right place. And this should now be happy. And we should be able to do go run. And pipe it into JQ again. And it all still works. So we've now got a much nicer directory structure. We've got a working Proto-C code, and we can generate Go code. So that's the bare minimum of what you can do with Proto-C. But there will be more demos coming in a minute. So let's switch over. OK. So the way that we had our first revision of protocol buffers was basically that. We had a central protocol buffers repository. We defined our error types that we were trying to fix, and we started to think that we could also define our service-to-service contracts in protocol buffers as well. And what would happen is an engineer would come along. We need to make some changes to the protos. They'd make the changes locally. They'd generate the code locally. They'd push it up to the repository, open a PR, get it code reviewed, and we'd do a release. And then another engineer would come along and pretty much do exactly the same process. And this can work absolutely fine for small teams. But the issues start to come up when you start to scale, as Banked is currently doing. So we're going from a small engineering team to a much larger engineering team. So we started to have some problems with using Proto-C as we were, and most of those problems was that Proto-C is a great tool, but it can get complicated. So because we need to support Go, Ruby, TypeScript, whatever language we may want to use in the future, that Proto-C command could get really big and really complicated. We thought about using make to split it up into nicer commands. So we had make Go and make Ruby and make TypeScript and whatnot. But make in itself can be its own pain, especially some of the ones that I've written can be quite difficult to read, and it's difficult to onboard new engineers. So make doesn't kind of really fix this problem. And the complexity just gets bigger and bigger over time as you get more engineers working on it, more people start iterating on it, it changes a lot. So one of the things that we were lacking was we couldn't lint the protocol buffer, so we couldn't ensure that engineers were writing well-formed protocol buffers. So even though you'd have a pull request flow and process, we're all human, we miss things. So there was no linting on them, although there is a tool that you could use to do that. There's no backwards and forwards compatibility checks. So let's say an engineer comes along and says, OK, it doesn't make any sense that this field is at field number 2 anymore. I'm going to put it at field number 10. That's a backwards incompatible change. So if 2 versions of the services get deployed and one's running the new one and one's running the old one, they won't be talking the same. The IDs will end up in the wrong places, or even it would just error. So we needed a way to enforce that there were always going to be backwards compatible changes to our protocol buffers. And there's no dependency management. So you saw those well-known types, but let's say we also wanted to use something else. There's some other really cool tools out there for Proto-C, like a validation that you could add on to protocol buffers. There's no way to manage those dependencies that you might have. And also, what about differences between Proto-C and Proto-Gen star, or in our case, Proto-Gen Go? So a new engineer comes on board and they brew install all of the stuff, so they get all the latest fancy versions. But then another engineer who's been around for a while hasn't updated in a few weeks or months. The 2 versions of Proto-C should be backwards compatible in terms of what they generate, but they could have tweaked how the code gets generated and what it looks like. And so the diffs, when you're viewing the difference in code changes, would be very difficult to look at sometimes. So there were some problems with it. So Buff is a tool that they have said they have basically thought about all of these kind of problems so that we don't have to do that anymore. They've solved all of these problems. So they provide linting checks. They provide breaking change detection. They provide easier code generation, so easier multi-language support. You don't even need Proto-C installed on your computer anymore. They have a thing called managed mode, which we'll take a look at. It's a bit opinionated, but it's there to help make life simpler in your protocol buffer files. They'll do remote code generation for you, so you don't even have to generate code on your computer anymore. They can do all of that themselves. As I said, easier multi-language support. They also have a thing called a Schema and plugin registry. So you can upload your protocol buffers up to this centralized schema, a bit like GitHub, but for protocol buffers and plugins as well. And because they have that, you get dependency management. This is pretty awesome. And what this all gives us is consistency. That's the most important thing as your engineering teams start to scale and you all start working on protocol buffers and you'll start to add new things and new services and new contracts, you want to make sure that it's consistent, much like the linting talk earlier we had today, where you want to ensure that all your Go code is pretty much consistent from service to service. You also want to do the same thing for your protocol buffer files. So let's have a look at doing some buff build locally. So it would help if I change the displays. Okay, so demo 6, I'll delete these. All right, so we've now got some 3 new files in our directory structure. None of the protos have changed from before, they're exactly the same. We've now got a buff.yaml file in the root. This defines the linting, if you can't see that, it's all the way at the top. Might zoom in a little bit. So there's linting options that you can provide. You can use the default ones, but like the linting talk earlier, there's a lot of linting configuration you can give to buff, so you can tailor this to how you want your protocol buffers to be linted. And the same goes for breaking changes. You can really configure that and say, hey, I don't care about this particular breaking change option. I don't want to use it. So you have that. Then you have this buff.work YAML file. It's a little bit like the Go workspaces, but we're basically just telling it where you can find all the protocol buffer files, and usually that's just going to be in the current working directory. And then we have this generate file, so buff.gen.yaml, and this tells buff build what we want to generate. So in this case, we're just going to use Go, and we're going to use the same arguments that we basically gave Proto-C before. So in this case, I don't need Proto-C on my machine anymore, but I do still need Proto-Gen Go, because that's the thing that's doing the code generation, but I don't need Proto-C anymore. I won't brew uninstall it just in case. But so now what does this look like? So there's a few things. So if I run this buff build command here, this is just going to basically tell us what packages it's found. So it can see that buff has found that there's this bank.v1 protocol buffer package, it's found this Google protobuf package, and it's found this bank.payment.v1 package. So we're going to run bufflint, and because I haven't done anything bad, it should just not give me any problems. It says it's fine. But what if we break something? So let's come into here. Actually, let's do it in the errors one. So one of the main things is, as I said earlier, you want to make these messages title cased, but let's just, for fun, let's just define it as a lowercase message, like this. And then we'll run bufflint. And now it basically tells me that there's a problem with this, and it should use Pascal case. So we can undo that. It's okay. The other thing we can try out is the breaking change detection. So I'll change this field ID from 4 to 5 for fun. And then we'll go and we'll do this breaking change generation. So this command here tells buff.build to use git as the way it's going to do the comparison. So it needs to basically be given the path to your git repository, what branch it's going to use for the latest commit, and any subdirectories you want to tell it to look for the breaking changes within. And now it tells me that there's an error because I pretty much basically deleted a field. So field 4 no longer exists. So it's saying, hey, this field went away. So if we put it back, and everything is fine. So now we can run basically buff generate. And now we will have all of our Go code generated just like we had before. It will be exactly the same. So now we're going to make it a little bit more complicated. So what was that manage mode that I mentioned about? It's basically a way of making a protocol buffers a little bit easier to look at. So previously, you saw that we had these Go options everywhere, basically telling it the Go module path that we were generating the Go code for and its package name. But this can get error prone. If you're copying and pasting this around, and I've done this before, like there is actually a typo in one of our protocol buffer repositories right now where this was just typoed and it was named incorrectly. And that can cause a little bit of problems as well. So we kind of want to like make that common across everything. So the manage mode helps you do that by not having to provide that on every single proto file. So these proto files now no longer define that. And I'll also just delete these as well, just to prove. So that goes away. And this manage mode will also enforce that, that v1 and v2 and v3 and that version subdirectory structure as well. So it will expect it to be structured like that. And there's no other changes to the buff configuration. So we've just done that. So literally, all we have to do, again, is we just do buff generate. And then we get all of our protos again, and they're all put into the correct place. So, perfect. And that's all just done with that. So we'll move on to the next demo. So we'll make it a little bit more complicated, and we'll add some plugins now and some external dependencies. So again, most of our bank stuff hasn't changed, although I need to remove all of this stuff. OK, so we're in the clean directory. OK, so I talked about remote code generation before, and I talked about plugins and schema registries. So now what we've added to our buff YAML file is some dependencies for the Google APIs, so for like the Google API well-known types, and a new thing called Proto-C gen validate. So this will allow us to import this proto schema, and we can use it in our own to give our protos some validation rules. So what I've done is in our errors up here, I've said our payment ID really should be a string, and it really should be a UUID. So that's the validation rule that we want to put on it. Nothing's changed in buff.work. So now in our buff.gen has changed quite a bit now. So there's some new stuff here. We've changed completely over to remote code generation. This only works for Go at the moment, and I think maybe the recent TypeScript stuff. So this only really is applicable to Go stuff. So if you're using other languages, you still need to do the local code generation as well. So we're still using the manage mode, but we need to tell it to ignore or accept the proto-gen validate protocol buffer schemas, because basically what it's doing is it's renaming Go modules under the hood. And if you don't tell it to ignore this, it will mess up the imports. So you need to tell it to ignore this. So we're using the buff.builds Go remote code generation here. It's basically the same as you would do it locally. And we're also going to add gRPC in just for fun. On a side note, Banked at the moment doesn't use gRPC. That's in our roadmap to use gRPC. All of our services talk HTTP using REST, and the general idea was to switch to protocol buffers as a first step to define our contracts in a single place. And then once we get our service mesh in, we can start talking gRPC. So we're kind of like on the roadmap to getting to gRPC. And then we also have the proto-gen validate. The other interesting quirk here is that the schema, the proto files come from Envoy Proxy, who have made this, these protocol buffers, but they don't publish the plugin to buff.build for some reason. So, but somebody else has. So that comes from a different user. So that's why there's a mismatch here. That one comes from Envoy Proxy, and this one comes from this guy. So if we just run. Oh yeah, and the other thing that will happen, in fact, I might just delete it just to show you, show it happening. So now we've added some dependencies. We kind of need to update them, so we basically just do buff mod update. So that will go and download dependencies that we have in our buff YAML file, and it will generate this lock file. So it basically locks everything to these git commits and versions. So now everybody who uses this will all use the same versions of things. And then we can just run buff generate. So now it's doing remote code generation. It takes a little bit longer because it's obviously going somewhere else and to generate the code. But now we have all of our generated code in here. So we have our errors in here. But now we have this other extra stuff that's been generated in here. So we've got like this .validate go stuff. So that's all of the validation rules being generated in here for our types. And we've also got the gRPC stuff that's been generated here. So we've now got a ton of stuff that's been generated for us. And in the example, main code, what I'll do is show you how the validate stuff works. So here at the moment, I've commented it out, but we'll uncomment it. And then we'll just run this. So this will give us an error. So it gives us a invalid error, insufficient funds payment ID value must be a valid UUID. So now you can put validation rules, and they have lots of validation rules. You can say a number has to be less than or greater than this. You can provide all kinds of like different kind of validation rules on your protocol buffers. So you can start doing validation on those, which is super useful for us. And if I just if I get rid of this again and I run that, you get the standard JSON output. Okay, so we'll stop mirroring. So that's buff.build locally, and that's pretty much kind of how we have it working right now. So there are ways to improve it, though. So the way that we have it working is engineers will basically commit their changes just to the proto files now, to our protocol buffers repository. They'll open a PR. GitHub Action will basically go away, lint the code, check for breaking changes, and actually generate the code, and then commit that back onto the same PR. We can then open a pull request for a review. So the engineers basically only need to care about the proto files now. They don't need to care about the generated code, and it all just gets approved and then released, and that's pretty much the cycle we have at the moment. So the last demo that I have on this is just on showing you the GitHub Action stuff, which is pretty cool. They don't support at the moment Circle CI, which is a bit of a shame, but they do support GitHub Actions. So all of these demos here, by the way, are up here on a public repository banked GopherCon UK 2022. And demo 9 is where we're going to do the change requests. So provided all the Wi-Fi works fine. So we're basically just going to come into demo 9, and we're just going to add a new field. So string foo equals 5. And we're going to check out new branch. So just add that. Okay, and GitHub should give us a nice pull request link, provided the internet is working. Please, internet. There we go. And we'll just open this PR. Obviously, do something more descriptive than nothing. Okay, great. So come over to our GitHub Actions. So this has been kicked off. So this will do our linting and breaking change detection here. So whilst that's going off, I'll just walk you through what the GitHub Actions code actually looks like. It's pretty simple. If you wanted to do this in any other CI process, you can. You just have to do whatever you're doing buff.build locally. You just do it instead in your CI. So we just open that and demo 9. So we've got a couple of jobs here. So we've got our linting action. It's pretty simple. They provide this out of the box for you. So all you have to do is just use their buff build setup action. It sets up buff build. You give it a specific version of buff you want to use. So we've set this up here to use 1.7. So you can manage also the version of buff that you're using in a central place. So you can choose when you upgrade your version of buff if you want to. And then you just call their lint action. And you just say, I want you to lint demo 9, but obviously you would, if you usually just do the local, just do the dot for everything else. And the same with breaking change detection, we just set up buff again. But here it's a little bit more complicated on that against argument, where you have to tell it the git directory. So here we have to basically say, because it needs to be able to check it out. So we need to use our GitHub token to clone it, give it the repository path, and tell it the branch and the ref and the subdirectory and that stuff. So this command is a little long, but it tells it what it needs to do when it's doing its breaking change detection. So provided these two pass, we can then do the code generation. So again, we basically check out buff, we check out the code, and we get buff set up. We do some cleaning first, so we basically remove all of the existing protocol buffers that currently exist, and we'll just generate fresh brand new ones because we've already determined that it can not be a breaking change, and all then's fine. And then we literally just call buff generate, and that will generate the code as it did locally for me. And then we do some Go setup here, so we basically check out Go 1.18, and we'll do some Go mod tidy. So let's say we've introduced a new dependency, a new extension to protocol buffer, like that Proto-Gen validate, and that doesn't exist in our Go mod file yet, so we can just do a Go mod tidy on that, get that all updated. And then provided all of that succeeds, we'll just use this action by this guy here to commit all of this code back onto our branch with this commit message. And then provided all of this has gone green, which it looks like it has, head over to your pull request. Let's chat amongst yourselves whilst the page loads. Okay, so now our code is now generated and has been committed back on the pull request. So we can look at all the files changed. So we've now got all the new protocol buffer files here, and we can just see that this is the new thing that was added. And if you really want to, you can obviously load the diff for the proto files if you really want to, and they're there. But it's not particularly useful to look at those, and you can just review, approve it, or whatever, and get it merged into master. And then everything is there. The other cool, nice way of working this way is the new protocol buffer code gets generated onto your branch and committed. So if you wanted to test your protos locally first before you open to PR, you can basically obviously pull them down. So if we just pull, then we'll have all of the generated protos that are on that branch. So now everything happens in CI. You get a nice workflow, and all of the protos are now there. So you can iterate like this. So you could change the protos, push them up to GitHub, it generates them all, pull them down, test them out in whatever service you're developing them for, and keep iterating like that until you're happy with what it is, and then open the PR and everything gets merged in. So it's a pretty nice workflow that we have. But it's still not completely perfect yet. So I said this is how we currently work, and that's using buffer GitHub Actions. So the future for us using protocol buffers with buff.build is really, really bright. It's taken a lot of some of that pain away, and it has allowed some of our engineering teams to do some cool things. So Amelia, who I'm going to embarrass, who is sat down at the front at the moment, has written a plugin for us that she's published into our, I think it's private at the moment. Is it public? It's public. OK, it's public. It basically generates const values for all of the message paths for all of the messages that are defined. It's a nice plugin. It's easy to add in, and it's useful for our payments team to use. So Aaron, who couldn't be here, is also doing some stuff with gRPC Gateway on some of our newer services that we're writing. So he started integrating that in, and you can add like HTTP annotations, and you'll get a gRPC Gateway server stubbed out automatically for you. This is how some of our newer services are working, so that we can write them as if they're gRPC services, but front them with gRPC Gateway, so it still provides the HTTP APIs that we need to currently use the service. But then when gRPC is ready, we can just switch over. So the other thing that we're talking internally a lot about is package organization and usage of the Schema registry. So we're not using the Schema registry yet, but it would be cool if we didn't need that centralized protocol buffers repository. And each team could have their own protocol buffers repository and just upload their protocol buffers up to the Schema registry. And then any team that needs those could just pull them down. So for example, we have our payments team and we have our refunds team. Our refunds team probably needs to know a little bit about payments. so they can just basically take the payments protocol buffers schema as a dependency inside their domain. Another thing that we're really considering about is, could we use protocol buffers for our public APIs? At the moment, Bank defines its public APIs as an open API standard. These are documented on our developer documentation. But what if we replicated that in protocol buffers, generated those out as a public repository? We could then write really thin SDKs around that. So we could write a thin Golang SDK or a thin TypeScript SDK. And then our merchants could integrate with that really, really easily, and they don't have to write their own REST API clients anymore. Though we will obviously still support that if that's the way that some of our partners want to go down. And then we can use the API gateway, go through gRPC gateway if we need to, and just use gRPC like this. So this is something that's like, it's on our we really wish we could do this. And also we could use the protocol buffers to generate our open API docs as well. So from one thing, we could generate a lot of really nice tooling. So another thing that we've been doing recently is we've started using Nats Jetstream locally, well not locally, in our cluster for our messaging platform. So we've started defining our events as contracts in protocol buffers as well. But one of the things that our data team needs is to be able to read these. So instead of sending the messages using the binary message encoding format for protocol buffers, we send them using JSON. And we also enforce a specific message envelope as well. So we define that as protocol buffers. And we're using a couple of things here. So this any type basically means that this message envelope can basically take any type on it. So you could just put any kind of message on here, and it'll all get encoded for you, and you can decode it on the other side. This means that our data team can basically transparently read these messages and decode them if they need to, and then put them into whether it's BigQuery or whatever it's going to be in the end. I've probably gone through that pretty quickly. So hopefully, if you were on the fence about using protocol buffers and you weren't sure if you wanted to use them or not, or you've been hesitant, hopefully I've convinced you that buff.build can take a lot of the pain away that comes from using protocol buffers, and hopefully you can start to use them yourself. And that is an extremely powerful tool. They're basically fixing protocol buffers as far as I'm concerned. They're making some really good new tooling. In fact, there's a new thing that came out recently called Buff Connect, which is, I think it's a new gRPC and gRPC web kind of implementation. I haven't looked too much into it, but it looks really nice. So they've also got a web UI as well for writing protocol buffers. They're really fixing it all. So cool. If you have any questions, and thank you.